In this chapter, we're going to be getting into acids and bases and equilibrium, and a little bit on how those apply to the body. For those of you who have had high school chemistry, this should have been in there. For those of you who took 110, this is where the class is supposed to leave off, and we're going to review this. If you've had it already, great. It should be a nice, easy intro into the class. If it got cut short in 110, it's part of why we cover it here in 111. The rest of it has to do with the life applications that are important here in this topic. So 10.1 is just about acids and bases. So acids come from the Latin for the word sour, and of course you're familiar with acids in terms of many of the foods you eat, but especially things that taste sour like your citrus fruit and plenty of our beverages. There's multiple different definitions of an acid. We're going to see two of them here throughout this chapter. The first one is the Arrhenius definition. It's by far the simplest to apply, and the Arrhenius definition says that acids have hydrogens in them, so that when they dissolve they produce the hydrogen ion. Recall that hydrogen is an atom with one proton and one electron, and if it's become a positive ion then it's lost that electron, so we're really just left with one proton there in solution when we have a hydrogen ion. And then of course the other part of the acid is the anion piece here, and that can vary. Because there's charges here in solution, when they dissolve, they are electrolytes. As we said already, they have a sour taste. They will turn blue litmus to a red color. Litmus is an acid-base indicator, and we'll talk more about indicators later on. I will say there's another indicator called phenolphthalein, which I'm going to abbreviate here instead of spelling out. You'll get to see it later. Phenolphthalein goes between clear and pink, and at neutral pHs it's clear, so it would not change the color of phenolphthalein. It stays clear. Acids can corrode some metals. We'll also talk about some other reactions that acids can do, and acids are going to sting or hurt if you get them on you. When it comes to how we name acids, it depends on what kind of acid it is. If it's an acid that is binary, that means it's only made up of two pieces, a hydrogen and a nonmetal, or the one exception here, the cyanide polyatomic ion, a hydrogen and a cyanide there. We name them hydro-blank-ic acid. So in the case of HCl, you have the chlorine there. The blank comes from that ion, and the chlorine atom produces the chloride ion. We drop that suffix and replace it with "ide." Here we're going to change the suffix for an acid. We're going to call it an "ic." I think of the second word acid as a suffix still, so it's an "ic" acid, and we have that hydro there. If it is higher than binary, that is, it's made up of more than two pieces bonded to the hydrogen, more than two pieces total, a polyatomic ion bonded to the hydrogen. Then when there's a polyatomic ion, it depends on what the suffix on the polyatomic ion is. If it's the "ate" suffix, then we call it an "ic" acid. You'll notice the same as the "ic" up here, but we drop the hydro part, and so we don't have the hydro there. The fact that it's an acid tells us there's a hydrogen present, and then to be able to distinguish between the chlorine polyatomic ions here and the chloride ion here is why we have the hydro on the chloride ions, the non-metal ones. Anyway, the 8 ions become "ic" acids. The "ite" ions become the "us" acids. And then, of course, there is such things as per-8 ions and hypo-ite ions. Those become per-is acids for both of those. And so if you have that prefix on the ion, then you also get that prefix on the acid. I'll let you pause here if you want to take a closer look at this. This is also, of course, in your textbook, but I will point out here that all of the ones made up of two pieces or cyanide start out hydro, "ic" acid. All the others have a polyatomic ion, and so that suffix on the polyatomic ion over here is what gives us the suffix either "us" or "ic" acids there. So here we're asked to work these out. So here we have a hydrogen and a bromine. It's only made up of two pieces, so this is going to be the hydro-blank-ic acid. with that blank being the bromine. So we're going to have hydrobromic acid, that's this one. With this one here, we have the carbon 8 ion, and because we have the 8 ion, this is going to be the ic acid. And we don't have that hydro prefix there because of the polyatomic ion, because it's made up of 3 or more pieces. And so this is the blank here at the beginning is going to come from the carbon. So this is going to be carbonic acid. This is the same thing that you get when you dissolve carbon dioxide in water to produce your soda pops or the like. You get carbonic acid in there. A lot of times for flavoring, there's other acids in there as well, but carbonic acid is always going to be present in carbonated beverages. Here on this one, we've got bromine at our core here again, but this time it's made up of 3 pieces, so that tells us there's a polyatomic ion here. If you go look this up, this is the bromite ion, and because of that, this is going to be the us acid, and so we're looking for bromous acid, so there we have it. We defined acids, so here's bases. The Arrhenius base definition says that bases have hydroxides in them. There we go. And so there's an OH present there. You can see that here. For whatever reason, there wasn't a diagram showing the dissociation of this with the acids, but when this dissolves in water, we had a reaction equation like this, just not the diagram. It forms sodium ions and hydroxide ions, and so these are the hydroxide ions. Do keep in mind that this is just a particle representation. There's always limits to models. This is, of course, made up of 2 atoms, so if we want an atomic representation, we'd have maybe the oxygen here and the hydrogen attached to it there. It'd still have a negative charge, of course, but acids and bases, when they dissolve, dissociate, and for a base it produces the hydroxide ion. Getting into some of the properties of bases, they will taste bitter or chalky. A lot of your cleaners are acids and bases, so if you've ever had soap in your mouth, that bitter taste comes from the base that is there. They are also electrolytes because we produce ions in solution, and ions in solution can result in the ability to conduct charge. They will feel soapy or slippery if you get them on you, and that does not mean that they're dangerous. They usually don't, they usually don't sting the way that acids do, which kind of alerts you immediately to a danger, but they are hazardous to get on you if they are strong bases. They actually, the way that we make soap is by reacting a strong base. Lye actually happens to be sodium hydroxide is what lye is with animal fat. And so if you spill a base on your arm like sodium hydroxide, it literally starts to turn your arm into the same kind of thing as soap. And then for litmus, we get a color change to a blue color instead. And phenolphthalein, which I mentioned a moment ago, and there's your spelling if you want it. The abbreviation comes from the PH there and the TH there. But it will turn phenolphthalein from clear to pink. And so you do get a color change with the base. With the acid, it starts out clear, stays clear. Naming bases is fairly simple because it's just like naming other compounds. It's just whatever the cation is, hydroxide. And so there's no fancy rules to follow here with naming them. We're going to move on to some practice. So here we're doing some matching. You could kind of cheat here and just look at the ions and then just match those. I'm going to go through actually naming these though, because when it's not a matching thing, you're going to need to know which suffix to pick. So this is the nitrite ion, so that's going to be the us acid, so we're looking for nitrous acid, that's D here. This is calcium hydroxide, so it's a base. Calcium hydroxide then is E. And I suppose I'm going to list out here acid, base. The next one, we have a hydrogen here, so that's going to be an acid. We have the sulfate ion, so the 8 ion is going to be the ic acid, so sulfuric acid there, B. I suppose I didn't cross that one out. Here we have the iodate ion, so we're looking for the ic acid, so iodic acid, A, and of course that one is an acid because of the presence of the hydrogen there. Here we have a hydroxide, so this one's a base. In fact, this one was used as the example on our definition of bases, and process elimination as well tells us that this is sodium hydroxide there. Here's a summary of the acids and bases. I will point out, for whatever reason, they left off may sting from the acids there, but that's just a summary of the tables in your textbook, and you can pause if you want to get all the details. Here we're just going to apply those properties. So sour taste is going to be an acid, produces hydroxide ions in solution. That's an Arrhenius base. Chalky taste, that is also a base. Electrolyte is both. They didn't give you that as a choice, but A and B there, and produces H+ ions in solution. That is an acid.